So, let's talk about complex numbers. I cannot emphasize enough how important complex numbers are in electrical engineering. It's really important, it's really fundamental, and we're going to exploit the properties of complex numbers in ways I think you're very surprised to see. So, as always, we're going to define what a complex number is. We'll then learn how to add, subtract, multiply, and divide them. And then we're going to go into the important topic of the two different ways of writing complex numbers. It's called Cartesian and polar forms. Okay, so let's define a complex number. And this definition, I think, is a little different than you may be used to. A complex number is an ordered pair of numbers. So, A and B. An ordered pair. Now, what the ordered term means is that A comma B does not equal B comma A. The order matters. They're not the same thing. And similarly, if you have two complex numbers that equal each other, what that means is that A equals C and B equals D. So that's what the ordering has to do with things. And now we need to figure out how to do arithmetic with these numbers, what the rules of algebra are for them. And let's start with multiplying a complex number by a scalar. And so when you do that, what you do is you multiply each component, the A and B component, by the same scalar. Okay, I think that makes a lot of sense. If you add them, it's the same as adding the components of the two complex numbers. Again, keeping them separate. I think that follows. What isn't so obvious is where the multiplication and reciprocal formulas come from. Well, it turns out these are absolutely the right algebraic rules to use for multiplying and dividing, and we'll see why that is in just a second. But first, I want to point out something. This notation, A comma B, you should have seen before in analytic geometry. That's what notation you use to represent the location of a point in the plane. So here we have a point, and this is its location in the plane. Its x component is A, its y component is B, and this is just standard notation, and this also helps explain why the two components are kept separate when you have this geometric interpretation. We're going to call the x component the real part. We're going to call the y component the imaginary part. Okay? And that's just terminology, but where it comes from is the following interpretation of a complex number. We're going to write a complex number in the following way. A plus JB. And the J is an indicator of which way is the y component, which way is up. So this A plus JB means I can get to this point in the plane by going out A along the real part axis, the x-axis if you will, and then going up B units in the y direction, the imaginary part direction. And so this J simply represents which way is the vertical, the y component direction. So this is an interesting way of writing a vector sum. That's all that is. The fun comes when you define that indicator J to be the square root of -1. That's where things get interesting, and this helps us figure out where those multiplication division rules came from. Before I get into that, I have to point out, and you should be a little curious, why is J used to represent the square root of -1? You probably learned it as I was the square root of -1. And it's true, the world other than electrical engineers use I for the square root of -1, but not electrical engineers. We're special. We use J. And there's a historical reason for that. Turns out at the beginning of the 19th century, the French physicist Ampère wrote a fundamental paper on the mathematical physics of electricity. And he referred to current as intensité de courant, for expressing how much current was flowing, and so he used the symbol I for current. So according to him, I is the same as current. Well, it was toward the end of the 19th century that the importance of complex numbers came up. And so we can't use I because electrical engineers throughout the 19th century were using I for current. So we use the next letter in the alphabet. So it's only electrical engineers that use J for the square root of -1. So since you're in this course, you're going to use J for the square root of -1. And all I can say is, welcome to the Electrical Engineering Club. You're now an electrical engineer if you use J for the square root of -1. Fun to be in this exclusive group of really cool people. Okay, so let's go back and look at our arithmetic rules before in the light of thinking about them as A plus JB, a vector sum. So now multiplication by a scalar, well, I think it still makes sense. You have a scalar multiplying a sum. Well, the scalar multiplies each term in the sum. When you have a sum of sums, you just add them all up, and then we're going to group them by their x and y components, their real part and imaginary part components. That makes perfect sense. Now the multiplication rule is going to come up and make a whole lot more sense. So you have a product of two sums. We'll just use your normal algebraic rules that you already know. So A1 times A2, that's A1, A2, of course. And then you get A1 times JB2. Well, that's this, that's fine. So now let's say JB1 times A2. There's that term, that's fine. And the interesting one is JB1 times JB2. Well, rearranging that multiplication a little bit, that's got to be J squared times B1, B2. Well, J squared is the square root of -1, so that's -1, which means that's where this term comes from. So, in order to use the regular rules of algebra, when you represent complex numbers in this kind of vector form, this has to be the multiplication rule. So now where this reciprocal rule comes from, we're going to have to wait a little bit. I'll get to that in just a second. Well, now we come to one of the most important results, mathematical results for this course, called Euler's formula. Euler was a 18th century mathematician, the best and most famous mathematician after Newton. And he noticed the following thing. So take an exponential, e to the cx, and write it in Taylor series. And what Euler wondered was, what happens when c is the square root of -1, when it's j? Well, he didn't know what e to the jx was, but one way of looking at it is to use the Taylor series formula and see what you get. So here are the calculations that he made. So he just plugged in j for c everywhere in the formula, and just did the usual rules that we just talked about. So let's look at the even powered terms. 1 is 1, okay. This term, that's j squared times x squared. Well, j squared is -1, so that's where this term comes from. J to the 4th, well, that's j squared times j squared. So that's +1, so that's where that term comes from. Okay, let's look at the odd power terms. Jx, okay, well, there's Jx. J cubed is j times j squared. So that's j times -1. So you get a minus x cubed term here. So I think you can continue this on, and what the Taylor series says is that the real part, the x component, consists of all the even powered terms with an alternating sign. The imaginary part consists of the odd powered terms with an alternating sign. Well, lo and behold, Euler noticed right away, because he's a smart mathematician, that it has to be true that e to the jx is cosine x plus